Assalamualaikum and good day, Doctor. So today, our group is excited to present our CPU scheduling simulator for our operating system project. My name is Munif, and to make this simulation highly intuitive, our team decided to move away from abstract computing models and instead ground our system in a real-world scenario, a hospital emergency room sorting dashboard. So before I go into the details, we have selected topic 2 for our project, which is non-preemptive scheduling, SJF, and priority scheduling. So in our system, the doctor acts as the CPU, while arriving patients represent incoming processes. So we are simulating two specific algorithms here, which is shortest job first and priority scheduling. So a critical constraint of our simulation is that it operates entirely on non-preemptive rules. So in real operating system terms and in our ER sorter, this means once the doctor begins treating a patient, they cannot abandon them to treat someone else, even if a more critical patient walks through the door mid-treatment. So the current task must finish its burst time completely before the scheduler re-evaluates the queue. So to show you how we build this engine without relying on basis inaccurate sorting scripts, I will hand it over to Daniel to explain the underlying system architecture.
Assalamu alaikum. My name is Dani Iman Hakimi, and I'd like to thank Munif for the intro earlier. So yeah, here comes my part with the core engine architecture. As the system architect, I'll walk you through our core engine logic to prevent a common future-seeing CPU flaw where systems accidentally schedule tasks before they walk into the door. Our architecture relies on 4 synchronized mechanisms: the virtual clock, dynamic ready queue filter, first come first served tiebreaker logic, and idle time mapping. So first off, we have the virtual system clock. We initialize a current time variable to emulate chronological CPU cycles rather than using real-world time delays. So yeah, it's nested within the while loop here, and yeah, this allows the kernel to simulate hours of triage operations immediately, whilst preserving the actual clock tick logic. Moving on to our next core, which is the dynamic ready queue filter. We have the pending.filter line here, which ensures the isolation for time. The scheduler remains completely blind to any patient until the virtual clock reaches the exact timestamp. So yeah, it just stops the system from looking forward. Moving on, we have the first come first serve tiebreaker logic. So we handle algorithmic collision. So if process parameters match exactly under SJF or priority mode, like you can see here, this is for SJF, this is for priority, it falls back to the tiebreaker right here. And yeah, it's based on the arrival sequence to guarantee absolute processing equity. And as for our last core, we have the idle time mapping. It shows how we map CPU inactivity. So when the waiting room is empty, math.min over here, to the left, yeah, scans the remaining timeline to find the upcoming arrival. It logs that precise duration gap as the idle block that you've seen in Rafiq's demonstration in the coming bit. So yeah, to see the engine run live, we'll see Rafiq run the demonstration right now. Thank you.
Thank you, Daniel. I'm Rafiq, and I'm going to run our master test dataset live to show how our interface responds to these non-preemptive scheduling algorithms. Let's add our 4 team members as patient to the triage system. Now that we are all registered in the history log at the bottom, let's watch how the scheduling order changes. First, I will click run shortest job first. So here, I am Rafiq, executed immediately at 0 millisecond because I was the only patient in the room. When my treatment finished at 5 millisecond, both Najmuddin and Munif has already arrived. Because Munif has a shorter treatment duration of 3 millisecond compared to Najmuddin's 8 millisecond. Our engine scheduled Munif next. Also, notice the grey block level idle here. After Najmuddin finished at 16 milliseconds, the emergency room is empty until Daniel walks in at 20 milliseconds. The engine cleanly tracks this 4 millisecond dead zone visually. Now, let's clear our workspace using our custom reset simulator action. Running the exact same data under priority scheduling completely changes the execution block sequence. When my task finishes at 5 milliseconds, the engine evaluates the room and selects Najmuddin to go next instead of Munif. This happens because Najmuddin holds a critical priority ranking of 1, whereas Munif is ranked at 2. I will now pass the floor to Najmuddin to analyze the core mathematical outcomes of these two simulation variations.
Thank you, Rafiq. My name is Najmuddin and I will be breaking down the final performance metric derived from our terrain simulation run. So, by outputting our runtime calculation direct into an organized land table view, we can clearly evaluate the structure trade-off of this algorithm. Under our shortest job first run, the system achieved an optimized average waiting time of just 1.75 milliseconds and average turnaround time of 7.25 milliseconds. However, when switching over to priority scheduling, our systematic average waiting time climbed to 3 milliseconds and turnaround average rising to 8.5 milliseconds. So, this result perfectly illustrates the theoretical core of CPU architecture. Shortest job first is mathematically proven to be the most efficient strategy for minimizing overall wait time across a system. Yet, it introduced the critical problem of process starvation. If short tasks continually stream into our ready queue, a long task like 8 millisecond duration block, it could face an infinite delay. In contrast, priority scheduling sacrifices systematic speed to ensure the urgent, high priority tasks are guaranteed immediate resource allocation, regardless of how long their process. So, to conclude our project presentation on behalf of Fast Survivor, our simulation has successfully achieved all core objectives. We have demonstrated all the objectives. CPU scheduler can be accurate model using a strict non-preemptive logic, a synchronous system clock, and programmatic edge case handling without relying on a look-ahead shortcuts. Through this software engineering exercise, our team has gained a profound understanding of how operating system kernel manage scheduling green locks, compute metrics, and balance performance against utility constraints. That concludes our project walkthrough. Thank you very much for your time and guidance through this semester, Doctor.